Okay, welcome to class meeting 17 of EECE574, the graduate level probability and random processes. There is one announcement that I have updated the handout for this Peebles chapter 6. So you can go to the course homepage from schedule and download. You'd better update the lecture note posted here. I still have kept the previous link, which contains the error about what I'm going to correct today. So I'm sorry about the confusion. Probably you remember last time at the end of the meeting, I kind of covered the material very fast, murmuring a lot. And one of the reasons is that there was a mistake in the handout. So today I'm going to correct it. Anyway, the topic last time we were talking about was the mean ergodic in the mean square sense. So let me start by reviewing what that means. So we are given a random process x of t, and we assume that this random process is at least y-sense stationary with finite power. So what does that mean? Y-sense stationarity. Your ensemble averaged random process is a constant function. So let's denote it by x bar. Got it? So this x bar is a constant function. So at any time instant t, the value is x bar. Second one is that since we assume that the random process is y-sense stationary, there exists autocovariance function that should be originally function of two variables is what? Is replaced by a single variable function of time difference tau. Okay. So we start from these two assumptions. Of course, we need more technical assumptions to make the interchange between two limit operations, including integrals, possible, but that seems beyond the scope of this course. In many cases, we assume that the change of integral is engineering sense okay. But if you attempt to prove something very rigorously, you need tremendous amount of mathematical knowledge to justify that. Sometimes you will feel a kind of brick wall with very large height. So in that case, I may be helpful to advise you. So wherever you are, whenever you are, if you confront that kind of mathematical difficulty, I may give you a piece of advice that may give you a breakthrough, or they may give you circumvent that situation to make a progress in your thesis or your project. Got it? So as far as I'm alive, you can always contact me to ask the material. I know the pain of very rigorous mathematical proof for engineering based PhDs and masters and undergraduates. Okay. So anyway, the start point is that anyway, we assume at least y-sense stationarity. For example, if mean function is not a constant, then ergodicity means nothing, because what we are going to do is that given that we are talking about mean ergodicity, mean ergodic, if. So here goes the definition. So ergodicity is a kind of very restrictive form of stationarity, which means that in a narrow sense, you have a set of random processes, you have a small subset of stationary random processes. In this case, Y-sense stationary random processes. And inside it, we are talking about mean ergodic in the mean square sense. Got it? So here, what we are going to do is that we take the time average. And from this time average, we want to obtain what? We want to obtain the statistical average, this one. Got it? So what we want to prove is this limit relation. Limit of this function parameterized by t converges to that one in some sense. Okay, just a second. Is it true? Mean ergodic in the mean square sense. Yeah, I believe so. Just a second. Something's still not correct. Let me. Yeah, I'm correct. So here I remind you that this is a random variable parameterized by t. So for example, if you choose every integer for this t, now you have a sequence of random variables. And you want to prove that sequence of random variables converges not only to a random variable, but also to a constant random variable. Got it? So this is this requires a kind of a type of convergence definition. So here, in the mean square sense, then if the convergence, this convergence is in the mean square sense, we are going to say that the random process is mean ergodic, because we could get the mean values, ensemble average mean value of the random process from the time average. Got it? So this is a definition of mean ergodic. So the ensemble average mean can be obtained from time average in the mean square sense. The convergence is in the mean square sense. And also, I want to remind you that the mean square sense convergence is what? So we take this guy and we take that guy and put them together like this. We subtract left from right. And mean square means mean and square. And what is this, by the way? This is now an expectation of some random variable, right? The argument is random variable, so which is a number. In this case, real random process we assume, so it's a real number. However, it's still parameterized by t. So this is a real number parameterized by t. And again, we may choose capital T as a positive integer. Then we have a sequence of real numbers. That sequence must converge to 0 by the definition of the mean square convergence. So in what follows, what we are going to do is simply prove this one. Last time, I failed to show you what exactly we are going to prove. And I put many errors there, so I'm sorry about that. So this is what we are going to prove today. Actually, what we are going to prove is that what kind of condition enables this convergence possible, given, for example, a Y-sense stationary random process. Got it? So let's see. First thing is this one. We define this one. we define this one as a sub x comma t. Last time, I put a lot of mistakes. Like here, I put infinity, blah, blah, blah. But anyway, I've corrected. Got it? So, as you see, this one converges to that one. Same as this one converges to that one, right? Now, exactly matches. So, what we do is that we define this guy, right, as a sub x comma t. And what do we need? We also need this one, but we already defined this as x bar, right? Ensemble average as x bar, because we assume y-sense stationarity of random process, and that is x bar. And interestingly, expectation of this a sub x, this one, expectation of this guy is also what? You see? Is x bar, right? Right? Be careful. There is no limit. I just took the ensemble average of the first term here and put the definition and exchange the order of integration and expectation. And from the y-sense stationarity, this integrand becomes x bar. Constant averaged any interval is constant itself. And again, this second term by definition is x bar. What does that mean? Actually, this one is left term minus left term's expectation. What does that mean? If you have a random variable, for example, y, and its mean is subtracted and squared and expectation is computed, what do we call that? Variance of the random variable, right? So the left-hand side, entire left-hand side is merely the variance of a sub xt. Got it? Do you understand? So here, we want to show this tends to infinity at 0 as t tends to infinity. And just found that under our simple assumption of y-sense stationarity, this is nothing but the variance of this random variable. So we just need to compute somehow the variance of this random variable. And we need to find the necessary and sufficient condition for this variance to converge to 0 as t tends to infinity. Or for sufficiently large t, variance is close to 0. Got it? So that is our goal. Last time I presented you Chebyshev inequality and Markov inequality. That was okay for the review. However, what I have found after the last meeting is that the Peebles textbook somehow mixed up the mean ergodic in almost sure sense and mean ergodic in the mean square sense in the proof. So I also was tricked. Here, we don't need Chebyshev inequality prove mean ergodicity in the mean square sense. We just need simple calculus, especially change of variable as we see. So anyway, we compute the variance of this random variable a sub xt. What is that? We just time average for the interval of length 2 capital T. That is a sub xt. We want to compute the variance of that random variable. And that's not that difficult. So here goes the variance of the random variable a sub xt. And by definition, we subtract its mean. And what is that? We simply can written like this, right? So it's an expectation of some integral squared. And as you learned in freshman calculus, you must be careful in this type of integration squared. The first thing is that you have to rewrite it as a product of two terms, two factors, right? And then since this is an integration variable, so-called dummy variable, you must choose different integration variables. For example, t and t1. Never use t and t. That confuses you a lot. Probably you've experienced many similar problems even in this QE if you have taken. Okay, I put a question proving Parseval's equation, and some students made the same mistake like that. Anyway, so here the trick is that the Peebles, this is equation is from Peebles textbook, use the t and t1. So the step missed is that here we have 1 over 2t, negative t, x of t bar dt. And here, apparently looking same thing, but now t1 minus x bar dt1. Got it? And then we put this together and interpret this one-dimensional integration multiplied as two-dimensional integration like this. Got it? So here, one-dimensional integration and one-dimensional integration. This is two-dimensional integration. So first, this is your trick of conversion. So your integration reason is now this square with area 2t squared. But here you have expectation of product of mean subtracted centered random process. And you remember we in the beginning assumed the random process is wise and stationary. So somehow you want to exchange the order of this expectation and two integration. So you take this inside the integral, and what do you have? Expectation of x minus x bar, x minus x bar. That is the auto-covariance function of the random process x, right? Since you subtracted the mean. This is constant function, which is same as the mean function in this case. So you have 1 over 2t squared, double integral, and now this expectation and this integrand combined to covariance of t comma t1 dt dt1. We haven't yet used actually wise and stationarity, which means actually this is a single variable function of t minus t1. So we can do something again. So here we have an integration in the two dimension, and we have a two-dimensional function that happens to be constant on what? Constant on this slanted region. So there exists a single variable function that satisfies. So even though these two functions have the same name, c sub xx, this is a two variable function and this is a single variable function. Wise and stationarity means that covariance function have a kind of twin that is in the different dimension, parallel universe that satisfies that one. What does that mean? If this argument is constant, the function value is the same. What does that mean? Then if you put that together, then you have this slope 1 lines. For example, on this line, the two-dimensional function has the same value. And what we are going to do is that we simplify this double integration to a single integration by using this property. Probably you've seen a lot similar problems in freshman calculus. So what we do is that we introduce this variable because each line has different t minus t1. So we introduce new variable, for example, tau here, and convert this double integral to a single integral over tau, right? Then what happens? Since we have this square, and if we define this as tau, then tau range is what? Here, let me use t and t1. Just a second. Sorry, this is t and this is t1. Then what is this? T equals t1 plus what? 2t, right? Because this is t, negative t, t and t. So as you know from your high school math, this straight line is given by that. So which means that on this line, t minus t1 equals 2t. And you have many, many parallel lines. And here, this is t equals t1 minus 2t. So if you define this as tau, now tau ranges from negative 2t to positive 2t, right? So here you have a strange conversion of the integration interval. Up to here, you introduce the tau, and now eventually you have integral over tau. And after some manipulation, it's not that difficult. From here to there, from here to there and there to there, you do it yourself. It's not that difficult. It looks horrible, but if you do it step by step, it's a freshman calculus problem. So now you have this as your single dimensional integration version of your variance. Now let's interpret this one. What does that mean? So now we work on the tau axis, that is defined as t minus t1. And covariance function may look like that. And what is this one? This is multiplied to this covariance function. And it looks like if we have interest in negative 2t to positive 2t, then this one is simply a triangular function that looks like that. And this is one, right? If you plug in plus minus 2t, it is 0. So even if the covariance function has non-zero values outside this interval of length 40, your triangular function zeros the tail and also suppresses the values far from the origin, right? And you integrate this function and divide by the interval. So it's still, again, a kind of time average of the product of triangular function and your autocovariance function. But the time is now replaced by delay. So this is not a time average. This is a delay domain average. Got it? So delay domain average of the triangular windowed autocovariance function. That is the precise statement on this quantity. Now, what did we want to show? We wanted to show this variance, when t tends to infinity, converges to 0. And we know that, I told you that some function, time averaged, may converge to 0. For example, suppose you have a finite energy signal. Then what is the time average of the instantaneous power? You have a finite energy signal, and you compute the time average. So you have a finite energy signal, and you time average the instantaneous power. What was that? So let me remind you the definition. This is the definition of time average of the instantaneous power. I have just defined this function as a finite energy signal. Then what? This is 0, right? Sorry about that, 1 over 2t, time average, right? So this integration also can converge to 0. It's possible, similar to this one, right? So what we need is that just this integral converges to 0 as capital T tends to infinity. That is the necessary and sufficient condition under regularity conditions, necessary and sufficient condition for a wise and stationary random process to be mean ergodic in the mean square sense. Got it? So this condition, delay domain average over triangular windowed autocovariance function tends to infinity. This condition will be appearing again and again and again whenever we talk about mean ergodic in the mean square sense. By the way, there is one interesting inequality here. See that? This one. Now what you do is that you take this off. As you see, this triangular function is always less than this straight line, right? So from here to here, first, you replace triangular function with constant 1, and then you remove this division. And if t is sufficiently large, if you remove that one, you have also inequality, right? So it's obvious that the time average is upper bounded by the absolute value of the autocovariance function. If you want, let me do it step by step. So we have this one. And we always have, if this is finite, we always have the integral, right, is upper bounded absolute value of this integral. And second one is that you take this absolute value operator inside the integrand. So you have 1 over 2t probably you remember this inequality from your freshman calculus. And then I replace this one by 1. Right? And then for t greater than, for 2t greater than 1, you can rewrite that. Anyway, we are going to consider t very large, right? So we have this inequality, upper bounding that one. Got it? And then, what if this integral, when t tends to infinity, sorry, something's missing. Just a second. Sorry. should be 1 over 2t, I believe. Why this is gone? Yeah, just a second. Yeah, probably I had to stop here. Just a second, let me check. I removed all the mistake, but just a second. Okay, got it. So now this is correct. This is correct. So there should be 1 over 2t. Yeah, I'm sorry. So I shouldn't be deleting that one. Yeah, so I had to stop here. And now what I want is this one. If now this is now a kind of sufficient condition. The necessary sufficient condition is that one. Got it? This quantity tends to 0. Now a sufficient condition is this quantity tends to 0. Got it? And another one is that in order for this quantity go to 0, another sufficient condition is that this integral, sorry about that, infinity, is finite. Suppose this integral is finite, then the limit of this quantity is 0, right? Got it? For sufficiently large t, right? This is a very, very small number. And this is what? This is almost same as that one, which is a finite number. So as you see that, this infinite integral of absolute value of covariance function is finite, is a sufficient condition for the random process to be mean ergodic in the mean square sense. So let me summarize. It's very confusing, but a y-sense stationary random process, real random process, x of t is mean ergodic in the mean square sense if and only if, of course, there is under certain regularity conditions, if and only if 1 over 2t minus 2t to 2t, and you have a triangular windowing the autocovariance function tends to 0 as t tends to infinity. So this is the first result. And second, if the covariance function is absolutely integrable. So this is called the covariance function is absolutely integrable. Got it? Sometimes proving the second part is easier. Then it's mean ergodic in the mean square sense. Got it? So if I were you, I would check this one first. And if it is so, I'm done. If it is not satisfied, then I will try to put a triangular window and consider this time average. So this is a triangular windowed covariance function has 0 time average. Got it? Triangular windowed covariance function has 0 time average. So that was what I wanted to say. So I have found the Peebles textbook contains errors because it kind of messed up with mean ergodic with probability 1 and mean ergodic in the mean square sense. He kind of mixed up two proofs. That does not fit well. Anyway, so amazingly, for Weiss stationary random process, at least Weiss stationary random process, it was not that difficult. It turns out not that difficult to prove ergodicity in the mean. Okay, what does that mean? Let me repeat. From the time average of a random process for a sufficiently large interval, you can find the mean function value over Weiss stationary random process. It seems it's obvious, right? However, be careful. We observe only a single random process according to the theory. So we observe a part of a single realization of the random process, and we get some information about the ensemble average. In this case, it's the mean function. So even though we paved a very long way, rough way to see one very small ergodicity, it seems that it's obvious, right? It's Weiss stationary. So if you time average for a long time, then must be the time similar to the ensemble average value. It's obvious, right? So it's too obvious, but anyway, we will base on that and to extend a little bit more from now on. Before, let's review some examples, some very simple examples we've already encountered. So let's start from a constant random process, but this constant is a random variable. Now, for example, A is a Gaussian random variable, standard Gaussian, okay? So what you observe is this. Sample function is always constant, but this deviation from zero could be a random Gaussian random variable with zero mean unit variance. Now, is this random process is strict sense stationary? Yes, because strict sense stationarity is all about what? The choice of the time origin. It's translation invariant, obviously, right? So this random process is a strict sense stationarity. But I'm asking you this question. Is it mean ergodic? In any sense, is it mean ergodic? See that? What is its mean? Its mean is zero, right? I said zero mean unit variance, Gaussian random variable. But if you unfortunately leave a world that has this sample path realized, then from any time average of that one, you will never know the ensemble average is zero, right? So this random process is, even though strict sense stationary, but it's not mean ergodic. Got it? So definitely you have to remember this one. So this first one is here, example 1. Got it? So it's strict sense stationary, but not ergodic. So in many information theory theorems, starts like this. Given a stationary ergodic random process X of t. Got it? So they restrict their focus to a very small reason. But that is important enough for that theorem. Second, let's meet again the terrible random process. For example, R and theta are independent, Rayleigh and uniform 0 to pi random processes. Then now you know that it's a Gaussian random process. Surprisingly, Gaussian random process, and also what? Strictly stationary, right? You remember from the quiz, and you remember from some homeworks. Now, given that, of course, F0 is not a 0 Hertz, you can show that it's a zero mean strict sense stationary Gaussian random process. You've seen that a lot. And now, it is mean square ergodic in the mean. Is it true? So let's see. Suppose you have a single realization of random process. It's a cosine function with some amplitude and phase, right? Now, given the cosine function, now you compute the time average. What is time average of a cosine function? It's 0, right? You can integrate from some value and divide by 2. You will always have 0. And it's zero mean random process. So in some sense, okay, this random process is mean ergodic. There still left is whether it is mean square sense or not. In order to prove that, you need some math. You can directly start from the definition of mean square ergodicity, or you can use what we've seen here, right? So which one do you want to use? Does this work? What is the autocovariance function? Probably you remember that since mean is 0, autocorrelation function is same as autocovariance function. And in this case, probably the autocovariance function was some kind of cosine function of tau, right? You remember. So if you take the absolute value and take the integration of the absolute valued cosine function, is it finite? No, it blows up, right? So in that sense, this sufficient condition approach does not work. What about this? What about this? You have a cosine function and you put triangular window, and then you integrate. And then you divide by 2t. Then what do you have? It goes to 0. You can show that. So by using the necessary and sufficient condition, you can show this random process. Strict sense stationary zero mean Gaussian random process is mean ergodic in the mean square sense. Or confusingly, mean square ergodic in the mean. So this example 2 is here. Now, third example, suppose you have a zero mean y-sense stationary random process that has autocorrelation function, which is same as autocovariance function given by exponential function of absolute value of tau. So it looks like that one. It looks like a PDF of a Laplacian random variable. Now, it decays very fast as tau tends to infinity, right? Now, as you know that here, this autocovariance function is non-negative already. So it's same as this function. And also, if you integrate, the area is finite, right? So what does that mean? This means covariance function is absolutely integrable. Hey, I remember that. That is a sufficient condition, right? If it is satisfied, done. For what? To be mean ergodic in the mean square sense. So this third one is also here. Got it? So we've seen 3 examples where we can use, or we may not need in this case, but anyway, the necessary and sufficient condition and the sufficient condition. Now, let's shift our focus for a while to a discrete time random process. So far, we've only focused on the continuous time random process, and we consider the simplest form of ergodicity, mean ergodicity. Now let's do the same thing for the discrete time case. So mean ergodicity for the discrete time random process. The only difference is that time average is now not integral, but arithmetic average. But to make the interval symmetrical with respect to origin, usually they take some n samples from 0, that excluding 0, and some n samples in the negative direction from the origin. So we consider the entire 2n plus 1 samples. And our summation is from negative n to positive n. So this is defined, this limit, if it exists, defined as the time average of discrete time random process x of n. Got it? And what is this one in general? This is a summation of random variables. So itself is a random variable, now parameterized by capital N. So now we have a sequence of random variables. And if it converges to something, there should be a random variable. But we want the simplest form of ergodicity. This time average, we want to be the ensemble average of the random process. That is this one. So this is what? This is by definition, expectation of x of n. So time average, same as ensemble average, especially for the mean function. So first, our goal is to translate our mean ergodicity for continuous time random process to a mean ergodicity for a discrete time random process. That is here. And we make a step in the same way, and amazingly, we also have the same thing. The error is, I believe, still, yeah, this is not correct. Just a second. Yeah, probably we have to consider n. Yeah. This would be the correct statement. Okay. Yeah, again, pivot. So the discrete time random process x of n is mean ergodic in the mean square sense, if and only if its triangular time windowed autocovariance function has what? Has 0 time average. Got it? And what would be the sufficient condition if we exactly follow the same thing? The autocovariance function, now this is a discrete time function, is what? Absolutely summable, which means this is finite. So this is sufficient condition, and that is necessary and sufficient condition. So exactly parallel. Derivation is almost the same. So it's highly likely if I put a very simple quiz problem, I'll put that one. Okay, so you just apply and study both of them. Now, so far, we only considered the simplest mean ergodicity, especially in the mean square sense, for continuous time and discrete time random processes. Got it? And now we want something more. Only talking about mean function over at least y-sense stationary random processes looks too simple. We want more. We want to extract more information from a small chunk of single realization of a random process. So the first thing is that, okay, since mean is a kind of first order moment, let's move to the second order moment. And among second order moments of a random process, let's consider the simplest one. That is the power. Okay? So now we shift our interest to this one. By the way, what is this one? The name is the instantaneous power. This is called the instantaneous power of the random process, x of t. Now, let me ask you a question. If you choose some specific time instant, t0, what is this one? It's a random variable, right? Random process sampled at any time instant is random variable, right? But it's non-negative random variable, but parameterized by t. So actually, this is again a random process, right? So we can view this entire thing as a new random process. And we may say that, okay, let's say this is y of t. And I may talk about mean ergodicity of this random process y. Then may translate to power ergodicity of x of t, right? That occurs to our mind. And exactly what we are going to do is that. So here goes the definition. Given a random process x of t, what we want is this. The time averaged instantaneous power is somehow equal to ensemble averaged instantaneous power. So we have ergodicity. Time average corresponds to the time average equals the corresponding ensemble average. If this satisfied, then we call that the random process x is ergodic in power. But still we need some convergence type. And of course here, we only interested in mean square convergence. So if this holds in the mean square sense, then we call x of t is mean square ergodic in power, or power ergodic in the mean square sense. Got it? So first thing is this one, power ergodic in the mean square sense. So let's say an example again. So independent Rayleigh and uniform, typo, 0 to pi. So its strict sense station is zero mean Gaussian, right? And we've seen that it's not, it's mean square ergodic in the mean. We've seen again, right? The question is it mean square ergodic in power? And the answer is no. Why? Why? Why is it not? Even though we do not have any theorem, we can directly show this random process is not ergodic in the power. Why? So let's just consider the realization, sample path of that. So there are two random number generators for R and theta. And R is Rayleigh, right? So, and theta is uniform. So you have some cosine function with some maximum realized R and some value theta, right? Sorry, cosine, so probably. Yeah, I have to say this. No, that direction. Anyway, so this is a sample path. So you only observe a single sample path. So this is the important thing. Whenever you think about ergodicity, take a sample, take a single sample path and examine it and check whether there is some ergodicity or not. So here, this is a sample path with some R and theta. And what is the power of this sample path? You know that it's a cosine function with twice the frequency and mean is here, right? And you've seen this a lot in the circuit theory, right? When you calculated the RMS value of cosine function and sine function, same thing. So now this function is a kind of a sample function of y of t, here I defined, right? Now, you take the time average of y, which means that you take the time average of this cosine squared. What do we get? 1/2 of r squared, right? So time average of this sample path is simply this one. Am I right? Yeah. Now, my question is this one. From any realization, what you want is that this value, right, for any realization, this value wants to same as this one, but if we generalize the idea, the left-hand side is what? Is a random variable, right? The left-hand side is a random variable, as we've seen here. But we want the right-hand side same as the right-hand side, which is not a random variable. It does not make sense. So this strict sense stationary mean ergodic random process is not power ergodic. Got it? So from a single realization of this random process, you will never know the ensemble averaged power. Actually, another thing is this one. This is even, I should be careful. Okay. Yeah. Anyway. Now we want to recycle. We want to recycle the condition. In the mean ergodicity proof, we derive the necessary and sufficient condition for random process to be mean ergodic in the mean square sense. We want to do something similar for the power ergodicity. What can we do? Yeah, as I told you, you redefine the instantaneous power, which is a random process, as new random process y. And then just apply the mean ergodicity of the random process y of t. So let me write down here. So here, this is what? X of t squared is mean ergodic in the mean square sense. So two statements are the same if we define instantaneous power as y of t, new random process. And we know what does this mean. So this is necessary and sufficient for what? Yeah, you consider the time average, sorry, for t. Something like this, right? Am I right? Yeah. I believe so. Let me check again. No, sorry, 2t. So yeah, it doesn't matter in the limit, but let me be precise. Yeah. So this is a sufficient condition. This is a necessary and sufficient condition for Y to be mean ergodic in the mean square sense. So what we are going to do is that just replace Y with x of t absolute value squared. And another one is this one. Hey, anyway, we have squared something. So let's make it a special case of a more general one. So what we do is that, okay, this could be a part of a new proof. So W of t is mean ergodic in the mean square sense. And here we define W as x of t plus here strangely introduce lambda, it doesn't matter, and x of t is mean ergodic in the mean square sense. So here, if lambda is 0 and x is real, then what is this one? This is x of t magnitude square. So it reduces to this case. So the author, Peebles, just introduced this proof to include the power ergodicity. And it's now more general because this has a name, autocorrelation ergodic. So here goes the autocorrelation ergodic case. So autocorrelation ergodicity means that the time averaged autocorrelation equals ensemble averaged autocorrelation, especially here in the mean square sense. So the approach is this one. As I told you, we define a new random process W that is the product of the random process and its advanced version or delayed version you want. Got it? And we just derive the necessary and sufficient condition or sufficient condition for this random process, which is defined as this one, is mean ergodic in the mean square sense. Then if that is true, we can show that X is power ergodic in the mean square sense by taking lambda is 0. And as you expect, if we plug in, for example, here, let's replacing this as W, right? See that W is a product of two random processes or delayed version of random process. So 2, 2, 2. So we need fourth order moment, right, over random process. But anyway, as this says, if that fourth order moment satisfies that one, okay, then we are done. So it's hard to state here, but in some cases, if we can efficiently handle the fourth order moment of a random process, then we are done. We have the same condition. What we just need to do is that we put this product X into this W. And we show the same thing, nothing different. And especially that holds for lambda is 0, then we have power ergodicity. Okay. So unfortunately, the textbook does not provide a good example for the autocorrelation ergodic. But anyway, similarly, when we have two random processes, we have cross ergodicity as we have joint stationarity, joint Y-sense stationarity. The idea is almost the same, okay? So from two random processes, for example, Kospi stock market index or New York stock market index, you observe a part of single realizations of each random process. Now you want to make some prediction. That is usually ensemble average of the random process in the future moment. And what you want to do is exactly that one, to make a financial decision. And for that, you derive something. But there is a small mark, right? Liability, saying that this entire derivation is based on the correlation ergodicity, right? Cross correlation ergodicity of Kospi and New York Stock Exchange. And after 2 months, your boss says, hey, what's wrong? Why your profit ratio is negative, blah, blah, blah. I already put the liability remark. So that this entire derivation was based on the cross correlation ergodicity. And as you know, that is assumption which may not be true. Got it? Something like that. There is interesting thing which is not the part of our Peebles book, and this is from Stark and Wood. And there is ergodicity in distribution function. What does that mean? Given a random process, we know the first order PDF. What is the definition of first order PDF, second order PDF, third order PDF, blah, blah, blah. Suppose we are interested in the first order PDF of random process. That is definitely ensemble average related thing, right? So let me remind you. Suppose you have a random variable, a real random variable X. Then your CDF, right, can be written as an expectation of what? As I told you, any information about some ensemble information can be written as expectation, I once claimed. So I want to first show you what is that. And whenever you start, this is probability. You have to remember. CDF is simply the probability of an event that random variable is less than or equal to some specific value X, right? And this probability and expectation is usually linked by an indicator function, which takes value 0 or 1. An indicator function is usually written as 1 of something. And if this condition is satisfied, it is 1. If that condition is not satisfied, it's 0. If that condition is parameterized by X, usually we put X here. So here is X. But let me do this, okay? In this case, something like this. So be careful. I choose X as, for example, 5. I have chosen 5. And I want to use probability of event that X is less than or equal to 5. That is same as expectation of indicator function with condition X less than or equal to 5. Am I correct? Let's check. So here on the right side, expectation is value times probability. When value is 1, what is probability? Probability X less than or equal to X, right? Plus 0 times probability that this is great. So which is same as the CDF. Am I right? This is very important. Even though in most of the undergraduate course, it is not much emphasized, in the graduate level book, the use of indicator function appears again and again and again and again and again and again. So this is very important. But probably you've never seen in your undergraduate course, or your professor was mentioned, but you forgot. Okay, so we do the same thing for random process. So here goes, by the way, another thing. Here, the indicator function can be replaced by a unit step function like this. This may look strange, but this is my claim. Is it true? The CDF is same as this one. So this unit step function is either 1 or 0, right? So let's see. 1 times, when is 1? The argument is greater than or equal to 0. Probability, argument greater than or equal to 0. Plus 0, the argument is less than 0. Then what is this one? Yeah, it's same as this event, right? So you can use unit step function instead of indicator function. So let me repeat again. Probability of event can be represented by an expectation of a properly chosen indicator function or properly chosen unit step function. Especially when you have numbers, not some set of events, using unit step function is much easier to handle. But if you have some abstract event, indicator function is easier. So anyway, here comes another one. Not only the indicator function, that is a function of time. So we introduce that kind of strange unit step function or indicator function. And it may confuse you a lot. But if you take the average of this one, ensemble average of this one, you will see something interesting. So you take the expectation, ensemble average, then you will see that it's what? It's just the first order CDF of the random process x of t. Now, what you want is that this ensemble average of this indicator function is same as time average of this indicator function. What do you want to call it if these two quantities are the same? Ergodic in the first order distribution. Simply ergodic in distribution. Got it? So nothing special. If you slowly make steps, then you can extend the definitions of ergodicity in many, many, many directions. First, we considered mean ergodicity. Second, power ergodicity. Third, autocorrelation ergodicity. Now we have distribution ergodicity. Got it? So if this holds, let me recall that this one can be written as time average, statistical average, right? And we have distribution ergodicity. And amazingly, distribution ergodicity also has many convergence types. And of course, here in this chapter, we choose mean square ergodicity. And mean square ergodicity, the necessary and sufficient condition involves what? Covariance function. So amazingly, here goes the covariance function, or here correlation of the indicator functions, which turns out to be second order CDF evaluated at the same value. And you compute this is the autocorrelation function, and this is the mean function. So you subtract this minus this squared, and then put it here. And you've seen this again and again, right? And if this converges to 0, or if you compute the infinite integral without this triangular and absolute value of this one. So if this strange looking covariance function is absolutely integrable, then you have what? Distribution ergodicity in the mean square sense. Got it? So we are done. Okay. Next time, we will move to correlation function again. And that's all for today.